Section 7.4 is on page 453, talks about relative rates and growth. Well, this is an important section to cover before chapter 10 because we're going to be doing something like this. This is very close to L'Hopital, and 1 over 0 is infinity, and 1 over infinity is 0. Not necessarily 1. We could say as long as a is not infinity or 0, you know, where a is any number other than 0. Well, let's see how this works. This says if f grows faster than g, if f grows faster than g, if I take the limit as x approaches infinity of the quotient, notice f is at the top, I'll get infinity. And that makes sense. I could use L'Hopital to really prove that. We also say that g grows slower than a if the limit as x approaches infinity, and I have g at the top, and I get the limit to be 0. To get the limit to be 0, that means the denominator must be approaching infinity a lot faster than the top is. I'll show you how that works. And we say f and g grow at the same rate, something we need for limit comparison test. You know what that is. If I take the limit as x approaches infinity of the ratio of those two functions, and I end up with a number. So this is kind of like the rational functions back in the days, if you remember, when you graphed r of x equal n of x over d of x. And when you look for the horizontal asymptote, if the degree of the denominator was greater than the top, then the asymptote was 0. If the top was growing, if the degree of the top polynomial was greater than the denominator, then it was long division, and you called it oblique or slant asymptote. And if the degree of the top and degree of the bottom matched, it was the leading coefficient divided by the leading coefficient. Except here, we're not dealing with just pure polynomials, we're dealing with everything. So when they say, which of the following functions grow faster than e to the x? Which grow at the same rate as e to the x? Which grow slower? Well, all what you have to do is take a limit, and that will determine how this works. That is, I'll take the limit as x approaches infinity in any order. If I decided to take 10x to the 4th plus 30x plus 1 and divide that by e to the x, this is how it works. If I get the limit to be 0, that means e to the x is growing faster. Here they're asking, let me just answer the question, which of the following growing faster, same, or slower? If I get this limit to be 0, this function will be growing slower. And isn't this infinity over infinity by section 4.5? Derivative of the top, infinity over infinity, L'Hopital again, 120x squared divided by e to the x, infinity over infinity. And let me just move this a bit. L'Hopital again. Well, we knew we had to do L'Hopital 4 times. Now, you knowing that the top grows faster or slower, this is the way to show it. You can't say, well, exponential grow faster. I'm hoping that you know that exponentials grow faster. I'm sorry, I got carried away. What's the limit as x approaches infinity? Well, isn't that 240 over infinity, which is 0? Therefore, this function grows slower. So if the limit is 0, that means the denominator dominated the top. If the limit is a number, that means those are growing at the same rate. And if the limit is infinity, that means the top dominated the denominator, whatever that is. So anytime I want to compare two functions, I take the limit as x approaches infinity. You could do this in any order you want. I'm gonna match it with e to the x by putting e to the x in the denominator. And this way, if I get the limit to be a number, they're growing at the same rate. If I get the limit to be 0, e to the x is dominating, which means this is slower. And if I get infinity, that means that function is growing faster. Well, this is infinity over infinity, by L'Hopital, limit as x approaches infinity of product rule. 1 times natural log of x plus x times 1 over x minus 1 over e to the x. Well, that is actually, now I'm simplifying, I'm not taking the limit yet. That's natural log of x plus 1 minus 1. That will be infinity over infinity, so I hit it one more time, and that will be 1 over x over e to the x. And if I really think about that, that's the limit as x approaches infinity of 1 over x e to the x. That is 1 over infinity, which is 0. Therefore, slower. Well, it shouldn't be a surprise, because exponentials are the second fastest functions that we have in math. Okay. How about this problem? Here you really want to manipulate a bit, because if I take the limit as x approaches infinity of the square root of 1 plus x to the 4th over e to the x, taking a derivative of a square root is 1 over twice the radical times 4x cubed. You could end up doing this 5 times. It's much easier to manipulate the problem algebraically, such that, can't I say this right here is the square root of e to the 2x, since that's always positive, and combine those under one radical? That will be much easier. Oops, 2x. And I could say that is, by L'Hopital, right, square root of the limit as x approaches infinity of 4x cubed over 2e to the 2x, and by L'Hopital again, that is the limit as x approaches infinity of 12x, actually I could have reduced it by 2, make that a 6x, squared over 2e to the x under the radical. That's still infinity over infinity. In the least, I'm not using here the chain. Will take a derivative of this times 4x cubed and proceed, and the denominator will become square root of x times square root of 1 plus x to the 4th times e to the x, and every time you take a derivative you have to use the product rule. Few of those algebraic tricks could save you a lot of pain. So if it's infinity over infinity and that's a 3, I'll apply L'Hopital one more time. That is 6x, I keep on forgetting the 2, over e to the 2x times 2, and that's still infinity over infinity. I'll apply L'Hopital one more time. And that will be just the 3 at the top, 2e to the 2x under the radical, and that will approach 0, which means slower. And the next problem, again, limit as x approaches infinity of 5 over 2 to the x. Here we have a problem, because if I apply L'Hopital at the top, that's going to be 5 over 2 to the x times natural log of 5 over 2. The denominator will be e to the x. I could end up doing this forever. So whenever I'm dealing with exponentials, those are both exponentials, no need for L'Hopital yet. I could combine those algebraically, and that will be 5 over 2e. And I would say that would equal 2 times 2.4. That would equal 1. That will equal 0. Because this is 2 times 2.7, right? Isn't that 5.4? And you need to justify your work, of course. You say 5 over 2e is less than 1. And there it is. What does that mean? That means, again, I'm answering the question, is it growing faster, is it growing slower, or the same rate? It's growing faster. So an exponential match with an exponential could be a match, if not over or under. The fastest growing function is a factorial that's coming up. How about this problem? The same deal. I take the limit as x approaches infinity of e to the negative x over e to the x. That's the limit as x approaches infinity of 1 over e to the 2x. That's 1 over infinity, which is 0, therefore it grows faster. And what are we talking about? Oh, you know what I meant to say, right? I'm like, wait a minute, am I doing this wrong? Yeah, I'm doing this wrong. Grows slower. Okay, how about this function? Again, we picked e to the x. That's in order of speed. We have factorial, the fastest growing functions, exponentials, polynomials, radicals, and logs, in that order. To undo a very fast function, you need a very slow function, and to undo a second to third, you need also a slow, and we can't do a factorial, we can't undo a factorial yet. So, looking at part F, if I take the limit as x approaches infinity of x e to the x over e to the x, those undo each other, and that will be the limit as x approaches infinity of x, which is infinity, just because I need the space. Therefore, x e to the x, it grows faster. So anytime I say I'm talking about this grows faster or slower because I'm dividing by e to the x. And if I take this problem, if I take the limit as x approaches infinity of e to the cosine of x over e to the x. Well, here, this is the limit as x approaches infinity. Isn't that e to the cosine of x minus x, because those have the same base? Now, I have a couple of options here. I could say, you know what, the limit as x approaches infinity, this runs between 1 and negative 1, and this is negative infinity. So this is going to approach negative infinity, and e to the negative infinity is 0, therefore slower. If you have to prove that, you don't, for me, I'll accept that because that's where we're going with this. If you have to prove that, you could say, if you like, you could say, look, one way of showing that, let f equal the cosine of x minus x, take a derivative, right? And wouldn't this always be less than 0 for any value of x, because the negative 1 is going to dominate, right? You could say less than or equal if you wish, it doesn't matter, because this could reach 1 at its given value, so it could be 0 or negative. If the derivative is negative, doesn't that mean the function is decreasing? And if a function is decreasing, isn't that going to reach negative infinity eventually? That's one way of doing it. Another way of doing this also I want to mention is, this is like an official proof, you really don't have to take that route. You could do this. You could say, well, look, e to the cosine of x minus x, isn't that bigger than, so the smallest this could ever be is a negative 1, and the biggest that cosine could ever be is a 1. So isn't that 1 over e to the 1 plus x? Isn't that e to the 1 over e to the x? And if I take the limit as x approaches infinity of 1 over e to the 1 plus x, isn't that 0? And if I take the limit as x approaches infinity of e to the 1 that's a constant over e to the x, isn't that a 0? Wouldn't that mean that, therefore, that limit will equal 0 by the squeeze theorem. And I believe that is on page 70. Let me double check. By sandwich theorem, this book calls it, page 70. If you want to look at it, you can. To us, the limit will be sufficient, but you got to be careful and make sure it works. How about this problem? If I take the limit as x approaches infinity of e to the x minus 1 e to the x, wouldn't that be the limit as x approaches infinity? Isn't that like e to the x times e to the negative 1 over e to the x? Those cancel out. So isn't the limit of a constant the constant? Therefore, they grow at the same rate. Shifting a function left or right doesn't change its outcome. One more really quick to go. And that's pretty much the section. It says, order the following functions from slowest to fastest. Well, I'm going to claim one of those is the fastest. Right? Actually, one of those three. Because all of them are exponential. Well, let's see. 2 to the x, the base is a 2. Natural log of 2, the base is natural log of 2, which is smaller than 2. And e to the x has a base of 2.71. So I'm going to say, order the following from slowest to fastest. Slowest, second, third, and fastest. And if I want to show those, how would I show those? Well, now that you've seen this, I will say, well, let's see. If I take x squared divided by e to the x and take the limit as x approaches infinity, guess what? If I compare e to the x in the denominator, I should get a 0 for all of those. That's infinity over infinity, limit as x approaches infinity of 2x over e to the x, infinity over infinity, limit as x approaches infinity of 2 over e to the x equals 0. There, I've just proved that x squared grows slower than e to the x. So I'm going to do all the comparisons. Now I'm going to take the limit as x approaches infinity of natural log of 2 to the x over e to the x. Well, that's quick and easy. X approaches infinity of, if I combine those, natural log of 2 over e to the x. Well, this is what I know. I know that log base a of a to the x is x. So, if I'm looking at the comparison of those two, I know e is 2.71 and natural log of 2. Well, natural log of 2.71 is 1, so that has to be less than 1. So, this limit will approach 0 since natural log of 2 over e is less than 1. That's sufficient. So there, I showed it. Then I'm going to go to, so this showed, how about those two? Limit as x approaches infinity of 2 to the x over e to the x, and I'm going to do the same trick. And this is something that we're going to do a lot. And I'm going to say this equals 0 because 2 over e, which is 2.71, is definitely less than 1. And that's pretty much it for this section. Now this section is just to reinforce 4.5, and combination of this section, what you learned here and what you learned in 4.5 is what you need for chapter 10.